AP practice exam 2 key. It's the one either called early May or late April. So make sure you're picking that one. And just a couple things about this video and this test. This was a Princeton review practice exam from a little ways back, but I do think it parallels the AP FRQ exam quite well with the types of questions. And there is maybe the AP exam will probably jump a little bit around more within some topics. I think the questions kind of stay to one or two topics here. You might get 3 or 4 mixed in on the AP test, but overall it's a good match for what we're doing. The other thing I like about it is I think the time comparison is reasonably close. So I think, you know, how you're doing with this helps you manage your time for an AP test reasonably well. And then another thing is there's a few content gaps that we have, not many, but there are some, and this addresses it. And talking about content gaps, I think our first question is one where we have like a spec 20 or spectral photometer type question, which we did one lab on it, but we'll get more information here. And I think you can learn about that right here. Okay, so we get this first question. It talks about 1 molar solution of cobalt chloride. You have your volumes that you're trying to, that you're given. And then it just says, in order to achieve degree of accuracy in the table shown, select the following pieces of lab equipment. So we're trying to measure these volumes. And, to the nearest hundredth, we want a precise instrument. So looking at all these things, a beaker might be measuring, they might have increments of 10 milliliters, probably even bigger. 400 milliliter beaker would be even bigger increments. A 50 milliliter grad cylinder would have increments of 1 milliliter. So if I estimate one place past that, that would get me to the 10th. But the barrette measures to the nearest 10th. So if I estimate one place past that, that gets me to estimating to the 100th place. So that's what I would use in this measurement right here. Okay, next thing is, I'll just kind of scroll this here to keep this on screen. Then it asks us to find concentrations of these things. So I almost have to go back and look at my table, or we'll see that right here. And really, if I look here, here are some calculations, and I turn that out, and I'm looking at it, and this was a Princeton review. Sometimes they're a little sloppy with sig fig, so I just adjusted it for this big sigs. I don't want to get tied up in that too much, but we had 20 milliliters, okay, and it was 0.1 molar, and then I wanted to make 15 milliliters, so I put 15 milliliters of the 0.1 molar, and I put 5 milliliters of water. I think the easiest way is to go through dilution factor. 0.1 times 15 over 20 gives me 0.075. If I did the same thing for number 3, it'd be 0.100 times 10 over 20, which is 0.0500, and 0.100 times 5 over 20 gives me 0.0250 molar. All right, so that is what I did for that question there. And then if you get finger marks or smudge marks on here, this question here, that's going to increase the absorbance. It's going to make it less transmittance, more absorbance, because you're blocking the light. So that's what would be going on with question C. Let's see. This is one, you have this formula, Beer's law, A equals ABC. It's on your formula guide. We didn't talk about that at all, and I wanted you to become familiar with that. Probably, if I'm looking at things, I go, oh, C is for concentration. I know that's 0.1 or 1.0 or 0.100 molar, and I know my path length. And if I didn't know that, I would look at my formula sheet and see that B is the path length, and that is going to be 1.00 centimeters. I also know the absorbance, okay, the absorbance for each of the different things. I can get that from the table that we had earlier. So the only thing I don't know is this small a, or on your formula guide now, it might be like a Greek letter epsilon. Okay, so it's either a small a or an epsilon right there. So we got to come up with that and with units. And probably the key factor here is knowing that the units on absorbance, there are no units on absorbance. So then if I know the units on B, which is centimeters, and I know the units on C, which is molarity, A must be what? Centimeters to the -1 and molarity to the -1 to cancel out the units on B and C, giving no units right here. So that's why I know the units for the molar absorptivity constant A is M-1, Cm-1 in this case. And then I just took my data from the table before and I plugged in, and I'm kind of trying to go to that. Okay, so I got my first sample, I got the 0.485, or second sample 0.364. And I'm just going to kind of go down the list, and we can see this coming back here. All right, so the 4.85 was where it was 20 milliliters or 0.100 molar, and I could solve for A. Or I could do it for the next one where I got 0.364 and I had 15 milliliters, which was 0.075. So notice the absorbance gets less as the concentration gets less. It's proportional. That's why using either this first one at 20 milliliters or the 15 or the 10 or the 5 should all give about the same answer, which we get right here. So even though we haven't had that, you can see how we'd solve a Beer's law. A equals ABC, or if there's a Greek letter for that A, it's going to be the same thing. All right, now we're asked to plot absorbance versus concentration. So we can just take our data and plot that. And just looking at this, absorbance here and time on the axis right here. Now it kind of says have the right increments in this. This is off in this increments. This definitely looks a lot bigger than this. So hopefully you're not that sloppy when you draw things. I think you're given the absorbance and concentration, no units on absorbance, and you'll be tighter with this. They probably will give you some type of graph thing, but notice your point does go through 0, 0, and then you can fix these points and put them on a line. So you put your 4 data points on a line, plotting absorbance versus concentration, much like we did in lab. And let's see, then it says, what should the absorbance value be for COCl2 in the following concentrations? So you can look at this and say y equals mx plus b, and notice there's no y-intercept. Okay, so absorbance equals, the slope would be what, that small a, small b, the molar absorptivity constant times the path length, and then C would be your concentration. So when we solve this, for one of the data points, you could just figure out on the graph where your concentration is and move it up toward the absorbance. But then another one is like 0.18 molar, it's way up here, so you wouldn't be able to do that. So we'll show you how to do that with a calculation right here. And let's see, oh, went too far. It is right here. I just did a calculation, absorbance equals molar absorptivity constant, which we got. Oh, this is both the molar absorptivity constant times the path length, that's 4.85, and then I multiply that by my concentration, and I did the same thing right here. Okay, where did I get that 4.85? Better go back here without losing it, which, okay, I did the slope of the line is equal to this 4.85 times 1, which is still 4.85. Okay, so that is really the A and B term together. All right, and so A times B, which is this, times C, I can solve for A times B, which is this, times C, and solve for that right there. All right, let's look at question 2. And we got a butane. I think if you go to your test, you'll have a picture of this, but we got a butane lighter, and it's underneath an aluminum can with some water in it, and we're going to heat the water. Okay, and first off, we're asked to balance the equation. Princeton Review didn't do this correctly. This would be the correct balance equation right here. But the heat absorbed by the water as you heat it is Q equals M or CM triangle T or MC triangle T, where delta T is the change in temperature. So 82.3 minus 25 gives you that. The C is the concentration. And then, that's the heat capacity, which is 4.18 joules per gram degree Celsius. And then M would be the mass. Now notice you have water, which is 1 gram per milliliter, and you have 100 milliliters. So 100 milliliters times 1 gram per milliliter is going to be 100 grams. So now I can solve for this. I know it's 100 grams. I know this is 4.184. I know my change in temperature is the difference between these two temperatures. And I'm going to go ahead and plug that in. And I get 24,000. That would be joules, or it'd be 24 kilojoules. Okay, I think we had 3 sig figs. View is kind of sloppy with that sometimes. So it'd be 24.0 kilojoules with the right significant figures. Now it says determine the heat of combustion for butane. So we got to take that kilojoules we're getting, divide it by the number of moles of that we burned. Well, if we know the grams of butane burned, we can divide that by the molar mass to get to moles. And then we just take kilojoules per mole right there. Notice with an exothermic reaction, your delta H is going to be a negative number. It's not asking the amount of heat released here. It's actually asking for a delta H value, which is negative in an exothermic reaction and positive in an endothermic reaction. Okay, finally, they give you some other question, and it says, talks about the density of butane. Okay, well, if we know the milliliters, these 5 milliliters, we know the density, we can figure out the grams. If we know the molar mass, we can figure out the moles. And if we know the heat of combustion, which we figured out in the last problem, it's 2,700 kcals per mole. It talks about heat emitted, so I'm not really worried about the sign. And I just round that to 2 figures, and I say 130 kilojoules of heat emitted in this question right here. And then finally, the overall combustion, or not quite finally, we know this is an exothermic, and it says explain this in terms of bond energy. So there's a couple ways I can look at this, and I kind of address it 2 ways because I'm not quite sure of the question. I'm thinking about, here are my reactants, here are my products. Clearly an exothermic reaction, when I burn a hydrocarbon, my heat content goes down, okay, because it's an exothermic reaction. But if I'm talking in terms of, when they say bond energy, are you talking about bond dissociation energy? Again, these bonds are at lower heat content, but they're more stable. They have a higher bond energy, so they're more stable. So I kind of answered it from that perspective too, and said the bond dissociation energies is higher for the products and reactants because these are more stable. So I kind of addressed it from 2 angles because I was a little bit, I thought, not clear with the question that was asked there. Okay, finally, this last question is somewhat loose, but let's try to figure this out. It says one of the airs comes from heat, which is absorbed by the air. Okay, so why might it not be a good idea to do this in a sealed container? Okay, actually, now if you mean you're sealing up the can, that's not a good idea. Okay, you're heating it, that's going to increase the pressure, plus you might have more moles of gas at the end, and that could lead to an explosion. So I think that might be a safety concern getting to that. If you're thinking about it in terms of air, let's say, and this is kind of interesting, if you're performing this reaction, a sealed container would limit the amount of oxygen, and oxygen is supposed to be in excess, and that could affect your results. Okay, that seems a little bit more of a loose argument. My question to that is, why would you take the mass of butane later? Why don't you just take it before and after, and then you can measure that amount so you don't have to worry about that. The other thing is, if you look at the picture for the diagram, what's heating up, it's the heating source is under the can. Unless you're covering that whole system and not just the can, there probably should be enough oxygen to react with the fire. So I don't quite know where this question is going, and I think AP will be a little bit tighter with that when they're doing their questioning. This might be the better way to address this response. And again, if you get a question that seems kind of weird, answer it as best you can, move on. It's okay to do that. Okay, I think we'll stop here and I'll come back and do a couple other questions in the next video. So join in the next one. Thank you.